Hello again. Today we will talk about section 1.2. The title of section 1.2 is Combining and Transforming Functions. I think, again, this is probably review for some of you. So we'll go through it kind of carefully. But I'll leave a little bit for you to read and then ask me questions about it on your own. I don't normally like to do examples exactly as they are in the textbook, but with this one I decided I mostly would. So this is example 2 from your book, section 1.2. Suppose the annual revenue in millions of dollars of a company is given by this formula R of t equals 0.2 t squared plus 3t plus 5. The independent variable t is measured in years, and the value t equals 0 corresponds to the year 2000. Also in the problem, we're told that the annual cost, again in units of millions of dollars for the company, is given by this formula, C of t equals 4t plus 9. What we're supposed to do, and here I've changed the number slightly from the example in the book, is that we want to compute and interpret P of 1, where P of t is equal to R of t minus C of t. So, as you can see here in the definition of P of t, what we're doing is we're subtracting two functions. Okay, when I hear combining functions, what I'm thinking of is using my 4 basic operations, addition, subtraction, multiplication, and division, and just applying those operations to functions, right? So I might have 2 different functions that I want to add together, right? Maybe for like total cost, or in this case I'm subtracting. I'm doing revenue minus cost. And that creates a new function for me. That new function is this function that we're calling P of t. The way that we can compute P of 1, oops, this marker is no good anymore. The way that we can compute P of 1 is to do the following. We do this operation pointwise, is how we say it. And what we're going to do is we will compute R of 1 and then minus C of 1. Okay, notice that I'm just replacing my t value in the formula for P of t. I'm replacing it with 1 because that's the particular output value that I want. Okay, continuing the computation here, how do I find R of 1? Well, the problem told me a formula for R as a function of t. And this time I know that t should be 1. So wherever I see a t in this formula, I'm going to replace it with a 1. In other words, R of 1, what that turns out to equal is 0.2 times 1 squared plus 3 times 1 plus 5. Okay, that whole part in parentheses is the R of 1. The next part in my formula, what I'm told to do is subtract, and then I should subtract C of 1. We're going to put that in parentheses here. To get C of 1, I do the same thing that I did in order to get R of 1, but this time instead of replacing t with 1 in the formula for R, we're going to replace the t in the formula for C with 1. And so that, you can see, becomes 4 times 1 plus 9. Okay, here I want to remember my order of operations. I should do these computations inside the parentheses first, and then once I get those 2 numbers, I'll subtract the 2 numbers, and that final value will be the output, or the value of P of 1. Okay, I chose 1 this time. It makes the arithmetic kind of easy. 1 squared is 1, and so then 0.2 times 1 is just 0.2. 3 times 1 is 3, so we have 0.2 plus 3 plus 5. Okay, and then I'm going to subtract in the second parentheses. 4 times 1 is 4 plus 9. Right, that's going to be 13. We can see where we're going here. In the first parentheses, 3 and 5 is 8 plus 0.2. That gives me 8.2. And then I have to subtract, looks looks like 13 in the second parentheses. And so when we do this subtraction, we get minus 4.8. What are the units for this value? Well, the units for R of t are millions of dollars. The units for the cost are millions of dollars. When I subtract millions of dollars from millions of dollars, I still get millions of dollars. And so this negative 4.8 is in terms of millions of dollars. Okay, so we computed the value of P of 1. Right here is P of 1. And now we're supposed to interpret what this is, right, within the context of the problem. So this is something for you to, for those of you that are business students, I'm sure you're well aware of what this actually is, but in case we don't know, revenue functions like R of t arise in this course quite frequently. So do cost functions like C of t. Revenue is essentially the amount of money that this company is taking in for selling some products. C of t is the amount of money that it costs the company to create those products. And so if I look at how much money is coming in minus how much it took me to produce the products, I'm left with some amount of money in my pocket. Okay, and so P is profit for selling those products. P of 1, right, isn't the product like at any particular time, but it's the product at 1. And so what does a t value of 1 mean in this problem? T equals 1, t is in years, we were told that in the problem. We were also told that t equals 0 corresponds to the year 2000, and so t equals 1 will correspond to the year 2001. All right, so P of 1 equals negative 4.8 millions of dollars. The way that I can interpret this is that is to say something like this. In 2001, the profit for the company was negative 4.8 millions of dollars. It might seem weird that we're getting a negative here, but just keep in mind that the negative is a convention, and what it's telling me really is that the company lost money, right? So in 2001, the company lost $4.8 million in producing whatever the products are in this example. So again, in the course we'll deal from time to time with profit functions, revenue functions, cost functions, and the main definition is right here. All right, profit equals revenue minus cost. This is something we'll come back to over and over and over in the course. Subtracting is not the only way to combine functions. Like I said, right, we could add two functions together, divide two functions, multiply two functions. Another way of combining functions, which is a little bit harder for us to work with, is doing a process of composition. Now, you might have heard of composing functions before, but because it is kind of a bit tricky, we'll spend some time talking about it right now. So this is on page 19 in your textbook. There's a definition for the composition of two functions. So, given two functions, f and g, the composition of f and g is, it's going to be a new function, and it's defined by h of x, so this is the name of the composite function, is equal to f of g g of x. Okay, I said what we're supposed to say to describe this function, but I'll write it again just in case you missed it. Over on the right-hand side here, this notation, f parentheses g parentheses x parentheses parentheses, you read this as f of g of x, okay? It's a composition. What we're doing here is we're plugging the function g into the function f, okay? This is not multiplication. If you remember back to 1.1, with the definition of a function, we had to know what the inputs were, and we then also wanted to know what the outputs were. In other words, whenever you work with a function, it's important to understand what the domain is. It's important to understand the values of x that we're allowed to plug into a function. And a composite is no exception, okay? The domain of h, right, in other words, f of g of x, is all of those x values in the domain of g, right? I need to be able to plug x into g first, right? And in order for that to happen, I need the x to be in the domain of g. But then what happens after I get g of x? I turn around and I plug g of x into the function f. Right here we're kind of working from the inside out, right? So my domain is going to be all of those x values in the domain of g, such that g of x is in the domain of f. Okay, like your book points out, I think it is easier to picture a composition or the domain of a composition with kind of like a machine picture. My picture here won't be exactly what they have in your book, but the idea is similar. Okay, I'm going to think about three number lines, three real number lines. Okay, here's one of them. Okay, some real numbers here. And then I have some real numbers here. Another copy of the real numbers, and then I also have a third copy of the real numbers. Right, so inside each of these real number lines, I'm imagining a bunch of x's, just a bunch of numbers. And what I want to get a sense of is how a composition is working. And so let's pretend, right, that I have some x here, and this x maybe is in the domain of g. Right, so the domain of g is this interval, and so I pick some x, doesn't have to be like midpoint, but I pick some x in the domain of g. Since this x is in the domain of g, I can do g to it. In other words, I can plug this x into the function g. When I do that, I get an output, right? I get this point over here, which is called g of x, okay? And so in other words, my function g, right, is this arrow, this mapping. It took the point x and it gave me a new value, an output. In this real number line, I'm imagining the domain of f, right? So my domain of f is maybe here, right? This is the domain of f. And so, as long as this g of x ended up in the domain of f, I'm allowed to plug that number, that g of x, into the function f. Okay? And so if we do that, we get another output, right? And the output that we get over here is f of what we just plugged in, and we just plugged in g of x. Right? Some of these x's in the domain of g might not, when I do g to it, right, they might end up over here, right? So if this is my g of x, that guy is no good, right? Because he's not, I can't then do f to this point because this point isn't in the domain of f, right? So for the domain of the composition, I'm only interested in these x values that land in the right spot once I do g to them. Okay, so this composite value here, this f of g of x, kind of does both of these mappings at once. Okay, in other words, instead of taking 2 steps, the composite takes this number and just automatically sends it all the way over to the end. So this bigger arrow is the function f of g of x. All right, we'll see how what this looks like with some concrete examples of functions given by formulas. So this example, I think this is number 20 in section 1.2, similar to some homework that you have. In this example, we're told that a function f of x is given by the formula square root of 2x plus 3, and then another function g of x is x squared plus 1. All right, and what I'm supposed to do is I'm supposed to compute 2 different compositions. I'm supposed to compute the composites p of x, which is defined to be f of g of x. So that's what we'll do first. All right, and then I also, in a moment, will try to compute the function q of x, which is just the composition but in the other order. In other words, it's g of f of x. All right, so starting with p of x here, and working from the inside out, I have to do the function g first. In other words, up here I plug the function g into f. All right, so I take my function g, the x squared plus 1 function, and I plug it into f. What does plugging into f mean? Right, if I were to plug a number into f, I would replace this x and this x with whatever that number was. Okay, this time I'm not really plugging in a number, but I'm plugging in g of x. And so what is this going to look like? It's going to take x squared plus 1, and it's going to just plug it into the f formula wherever I have an x. All right, in other words, this is f of x squared plus 1. Right, I'm taking x squared plus 1 and then sticking it inside f. Because I have a formula for f, I know how to do this. Like I said, wherever I have an x in the f formula, I have to plug in the function g. And so it becomes the square root of 2 times the quantity, x squared plus 1, and then plus 3. Right, again, like I'm kind of thinking that this x squared plus 1 is x. Right? I'm treating it as my x, so to speak, right, as my input. So that's the answer. This is what p of x equals. Q of x, on the other hand, is composing these functions in a different way. Right? As it says, I want to do g of f of x. And so here, I should take f and plug f into g. That's kind of the opposite of what we did last time. Okay, so for this one, I'm going to take the square root function, right, the f function, and I'll plug it into the function g wherever I have an x. Okay, you can write it like this. This will be g of square root of 2x plus 3. Right here I'm taking f, which is the square root, and then I'm plugging it into the function g. By plugging it into g, what that means is I take whatever my input is, right? If my input is x, what I have to do is x squared plus 1. This time the input is square root of 2x plus 3, but the formula tells me what to do. I have to do the square root of 2x plus 3. I have to square that, and then I have to add 1. So this expression here is q of x. These two functions are different functions. We can see this if we just compute maybe a simple value. For example, what's p of 0? Right, if I plug in 0 for x in my p formula, that'll be the square root of 2 times 0 squared plus 1 plus 3. And so that's the square root of 2 times 1, which is 2 plus 3. And so this gives me the square root of 5, right? That's p of 0. However, when I compose the other way, right, when I formed this function q, this is what I got. And so q of 0, right, will be what? It'll be the square root of 2 times 0 plus 3 squared, the whole thing squared, and then plus 1. What you probably remember from some other class is that when you square a square root, those cancel. And so now what's left? 2 times 0 is 0 plus 3. So I'm just getting 3 plus 1, I'm getting 4. Right, that's what q of 0 equals. And so 4 and square root of 5 are not the same number. You can check that on your calculator if you want. But what I'm trying to say here is that, it's not a good one anymore. This is an important thing to keep in mind, is that the order in which you compose really does matter. You can't change the order for compositions. In other words, f of g of x does not equal g of f of x. Okay, order matters. This is not multiplication, this is composition. My markers are drying out a little bit, but I have a couple more examples that I want to do. The first one is number 21, and this is, again, similar to a homework problem. Again, it involves composition, but this time the problem is going to ask us to interpret what a composite represents in the context of the problem. So, number 21 here, 1.2, number 21. This is about surfboard production. That sounds fun. Let's let capital N of T be the number of surfboards a manufacturer produces during year T. If P of X is the profit in thousands of dollars, that the manufacturer earns by selling X surfboards, the question is, what does the composite function, what does the function f of t equal to p of n of t represent? So, well, let's think about it. The function f here is a function of t. T stands for time, and it's measured in years, okay? So this function is something that involves years. P we know is the profit. What was capital N? Capital N was the actual number of surfboards that the manufacturer makes during year T. All right, so capital N is a number of surfboards, and that capital N is being plugged into the profit. Does that make sense? Well, the profit, we're told earlier in the problem, is a function of x, where x is the number of surfboards that the manufacturer sells. And so N is also a number of surfboards. So it does make sense to plug surfboards into the profit function. So here, one way to write what this composite represents is this. Red is not going to work for me. This composite function is still profit. Okay, it's not the profit from selling X surfboards, but it's the profit from selling N surfboards. And not only is it the profit from selling N surfboards just any old time, but it's the profit from selling N surfboards during the year T. Okay, that's what this is. So it's the profit, again, in thousands of dollars. So it's the profit in thousands of dollars for selling capital N of T surfboards. And it's that profit in year T. So if I were to plug in a suitable T value like 5, that would tell me the profit from selling however many surfboards I sold in the 5th year. Okay, please read in section 1.2 about combining functions and pay particular attention to the composition section because that can be tricky. The other part of this section has to do with transformations, transforming functions. Not by performing the basic operations, but by scaling functions, by translating functions, by reflecting functions. So for that, I will do one example, but I mainly want to refer you to the tables in the book. And as transformations arise throughout the class, I'll point them out. So for transformations, I'd ask you to see the tables on pages 21, 22, and 23. So here's a real, hopefully this is a real kind of quick example. The question is this: how does the graph of g of x equal to 2x squared plus 3 relate to the graph of f of x equals x squared? All right, so in other words, what's going on here is that f of x equals x squared. It's kind of a basic function. That's our basic or standard squaring function. I think you're probably aware of that function already from the previous class. You might remember that the graph of x squared is a parabola that opens upward with a vertex at the origin. So in the xy plane, again, you've probably seen this somewhere. If you haven't, we can talk more about it tomorrow. But I think what you remember is that the graph of f of x equals x squared looks roughly like this. Okay, if you don't remember this, you can plot some points. In other words, if x is 1, right? F of 1 would be 1 squared, so that would be 1. So my output here should be at a height of 1. F of 2 should be 2 squared. In other words, I should get 4 for the output when I plug in 2. Right? If x is 2, the height is 4. Okay, so you could plot a whole bunch of points and then kind of connect the points and you would get this parabola shape. The function that I really want to understand, though, is a different function. It's not just x squared, but it's very similar to x squared. Okay? It's 2 times x squared and then plus 3. So how does 2x squared plus 3 relate to just x squared? Well, we can think about it one step at a time. To form 2x squared, what I should do is I should multiply every output from x squared by 2. Okay, so in other words, right, my first output that I plotted was 1, but now instead of being 1, that's going to be at a height of 2. Right, because I multiplied it by 2. Instead of getting 4 for my second output, I'm going to be at a height of 8. Okay, up here at a height of 8. So 2x squared, what this does, and it does it to all the points, what that does is it stretches my parabola, it stretches my graph, this is probably hard to see, it stretches the graph vertically by a factor of 2. Okay, so this is a vertical stretch by a factor of 2. But that's not the entire equation for g, right? Because I have the plus 3 at the end. Well, so how is that going to work? I know that 2x squared, I know what that does now, right? It stretches my parabola vertically by a factor of 2. It made it narrower. And then having a plus 3 here means that I should do the 2x squared, and then I should just add 3 to whatever that was. So let's try to go with a red. I don't know if this one's going to appear, but when I had my input of 1, initially for x squared I got a height of 1. For 2x squared I was up at a height of 2, but this time I need to then add 3, right? So instead of being at 2, I'm going to be at 5. Right? Yeah, it's kind of hard to see. For this value here, when x is 2, my initial graph, x squared, put me at a height of 4. When I multiplied x squared by 2, that bounced me up to a height of 8. And then the adding 3 would push it even further up to a height of 11. Okay? This vertex, right, that's at a height of 0. When you multiply 0 by 2, you get 0. So 2x squared also had a vertex at the origin. But then I'm adding 3. Right, so I actually have to, what I do to get 2x squared plus 3 is I take my 2x squared, which is my narrower version of x squared, and then I just translate it vertically in the positive y direction, in other words, by 3 units. Okay, so this is a vertical translation of 2x squared by 3 units in the positive y direction. Okay, maybe I'll make one quick plot of this and then I'll take questions about it tomorrow if you have any. Here's y equals x squared, and then 2x squared plus 3 is going to be a narrower parabola shifted up 3 units. So here's 1, 2, 3, and then it's narrower. This is the graph of g equals 2x squared plus 3. Okay, let me know if you have questions tomorrow. Try the homework.